Hello and welcome back. We continue our series in neural networks and deep learning, and we now look at recurrent networks and long short-term memory networks. So let's recap before we start here. So far we've discussed feed-forward networks in various combinations, for example, fully connected networks or convolutional neural networks. Here we have a, so we say, linear information flow. The information enters the network via the input layer, like the feature variables on the left, or in case of deep learning and convolutional neural networks, we feed in, for example, directly images. And then they pass through multiple hidden layers, and this is like the deep in deep learning, until we reach the output layer. So essentially, during inference, when we make an estimation about a new object, we pass the information from the left to the right. That means the nodes are connected in only one way. These are the weights. They connect the nodes from input to output. And this was the formula from an output node J in a given intermediate or output layer. We have the output that is given as a function of the input x, and the values of those feature variables, for example, are summed up as an average combined with weights. And then we apply the transfer function, and we do this repeatedly in the way we choose the setup of these weights and how many nodes and how many layers. This specifies how our feed-forward network or convolution network is set up in the network architecture and topology. However, this is good for learning direct mappings of an input to an output, but not enough for sequences. For example, the sun is in the sky, we naturally tend to fill in the blanks. Or, I grew up in Germany, I'm fluent in, the most likely word is German. Also time series data like sensor data where we capture values one after the other, and we might want to predict the next one. This is not enough to learn with feed-forward networks as such. Another application would be machine translation, like the German sentence, ich studiere Materialwissenschaften, would go to I study material science. And this also is very difficult to do with feed-forward networks, so we need a new approach. On a very abstract level, we can call this sequence to sequence. We have a set of input tokens, for example, shall we say, or words. Let's go with the example, ich studiere Materialwissenschaften. So each of these words would be, for example, an element of the input sequence. We can also do it, in principle at least, with images, so we would have pixels. So these tokens can be anything that is fed into our sequence encoder. So this encoder is at the moment an abstract entity that combines somehow the input into an intermediate state Z. And then this is decoded, this intermediate state, and we get an output sequence. For example, the English translation, I study material science. So how do we do this? First of all, we need to introduce recurrent connections. In a recurrent network, we introduce a backward connection. So the output of a neuron goes back as the input of the same neuron or a group of neurons or layer of neurons. So this allows us to learn sequences. For example, time series data, language data, and so on. So you can see here on the right how this happens. Before we had the input that passes through the network node into the output, and now the red arrow indicates that this is sort of branched. One part goes as before and another part goes back as input. So this introduces effectively a recursion. The input at step or at time t is now not only the feature variables x at the time of t, but also the output at the previous step, y t minus 1. So this means we need to modify our output formula for the neuron. We still have the transfer function, and now we need to expand this, what we had before. The first part is what we had before, x times the weight. We use the weight, the matrix notation here. And now we have the output of the time minus 1, the previous step, times a new set of weights. So the output at a given time t is now comprised as the forward part, shall we say, plus the recursion. How do we train these? It turns out we can do it with backpropagation, just as feed-forward or convolutional neural networks. But there's a catch, of course. We need to disentangle, or as it's called, unroll these recursions. And this is why it's called BTT, backpropagation through time. Of course, this poses a few challenges. Many recursions are needed for long sequences, but that leads to large unrolled networks in this modified backpropagation through time. So when we say that maybe big convolutional networks are difficult to train, this becomes even more difficult because we now have all these unrolled recursions. To put this concept a bit further, we can introduce a memory cell. Remember that we said that we have a hidden state, some function z in our encoder-decoder setup. So far we've just introduced a recursion. Remember the previous graph where we had the red arrow. Now we add a little box, and this introduces our hidden state. The hidden state is essentially some function that modifies the output before sending it back. Before, in the simple recurrent network, we were just sending the output of the node back as input. But nothing is stopping us from modifying it, and this is what the hidden state does. We introduce some arbitrary function eta, and this is some function of the previous times plus the input. And effectively, here we introduce some sort of memory for earlier elements in the sequence, because we can now choose how to operate on the output of the node. These memory cells help us to allow longer sequences, because we can decide what we want to remember and what is relevant to our sequences, and also decide what not to remember or to forget. So how can we now go back to our abstract sequence-to-sequence network? Before we discuss the top part, we have the input, for example, a German sentence, and that what was encoded to an intermediate state. So let's look at the encoder in a bit more detail. Here we have many cells that make up the encoder, and each of these words, for example, go into one cell, and then now we have these hidden states. And because the words are in a sequence, the cells have a natural sequence as well. And we pass on how these words, for example, develop to the intermediate state. And these cells encode, for example, then what we learn about sequences of words. On the decoder part, we do the opposite. Here we have output cells that correspond to the translated words. I study material science in our earlier example. Here we don't use the access input, but we start from the intermediate state. That gets fed into the neural network cells with their hidden states. And as the decoder progresses, these sort of cells disentangle the meaning of the sequence of the input words. One very efficient way of doing this is the long short-term memory cell. These are very effective memory cells, and the key idea is that we decide what to remember and to forget in long sequences. So our hidden state explicitly becomes our memory, where we have some sort of function that remembers what we want to remember at this previous time, and then compares what we had in our memory before and what we need to add to our memory now. And as you can see, this is one single cell in the sequence. You can see from the different functions and their combinations, the setup is fairly complex. However, it turns out that such a setup is quite effective in learning long sequences. On the other hand, the whole approach is largely superseded by attention transformers these days, but this network architecture and the way of dealing this lay the groundwork of building on those.